All right, yesterday we talked about inverse functions, and the reason we did is because this whole unit was talking about exponential functions and logarithmic functions, and those are inverses of each other. But the things we're talking about today are not inverses, so keep all that inverse talk sort of on hold in the back of your mind. What we are going to learn today is the basic exponential function. We're going to talk about the two different ways it can be graphed, and we're going to talk about how to transform those graphs. So you have a notes page here where the basic function is y equals b over x. And this is why, let me tell you why these are called exponential functions. It's not just because there's an exponent in the function. Okay, so because, for example, this we call a quadratic, it has an exponent. We do not call that an exponential function because its exponent is a number, an integer. This exponent in this function is a variable. And so it's like we call rational functions because their variables are in the denominator. They don't have just numbers in the denominator. They have an x in there somewhere. Same thing for exponential functions. It's not just that it has an exponent, it's that its exponent is a variable. And the b stands for the base, and the base can be any number. And that falls into two different categories. When the number is greater than 1, we have this left-hand side graph is the behavior of the y's. When b is between 0 and 1, meaning it's a decimal or a fraction, it's a small number, the graph looks like this right-hand side graph, okay? We call it decreasing because what are the y values doing? As x goes to infinity, what's its end behavior? Well, y is decreasing. On the left graph, as x goes into infinity, what is y doing? It's increasing, okay? It's going to positive infinity. So this is the behavior depending on the base, okay? So keeping all that in mind, what I would like to do first, before we talk about these general forms, is I want us to actually generate our own exponential function with a specific particular base. So on the back of your notes, we're going to do this. We're going to look at the functions y equal 2x Okay, this is an example where, y equals 2 to the x. This is an example of b greater than 1. And I want us to generate some points. So give yourself a table, and we're going to see what happens for these values of x. So when x is negative 3, and I plug it into the function, that gives me 2 to the negative 3. Okay? Well, when you have a negative exponent, the rule is to flip and make the exponent positive. So that means 1 over 2 to the positive 3, which is 1 over 8. So when x is negative 3, y is 1/8. Okay? Similarly, with negative 2, we have 2 to the negative 2 is 1 over 2 squared. That gives me 1 over 4. So when x is negative 2, y is 1/4. You try negative 1 while I do negative 1. Okay, hopefully you got negative 1 1/2. The next 2 points are important because they have a consistency no matter what the base is. So when x is 0, and I plug it in, that gives me 2 to the 0. Remember that anything to the 0 power equals 1. So 0, 1 is going to be a point on every exponential function, because no matter what your b is, When you put 0 for x, it will simplify to 1. So this is a special point right here. That will be on every exponential graph. So then when I plug the next value, 1 in, I get 2 to the 1, which is 2. This is another special point because it won't be the same for every single exponential function. What will be the same, though, is that for 1, anytime x is 1, your y value will be whatever your base value is, because you're going to be putting 1 in for x, and that will just give you your base. Okay, so these 2 points have some consistency throughout every graph. And then when I plug 2 in, I get 2 squared, which is 4. So that gives me 2, 4, and then 3 squared is 9. So that gives me 3, 9. So let's talk about the graph here. Okay, you don't have to be super awesome at the graph, but we're just going to talk about the behavior of it. And I'm just going to be general. Negative 3 1/8 is going to be here somewhere. Negative 2 1/4 is a little bit higher. Negative 1 1/2 a little bit higher. 0 1 1 2 2 4 and 3 9 is going to be way up here. So what happens is it increases slowly, 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 and then boom, it just shoots up. And what's going to happen as x goes out to negative infinity, it is going to approach this line, but never ever cross it. So it's got a horizontal asymptote at y equals 0, but it will never actually equal 0, no matter what value you put in for b. So notice here, when b is negative 1, y is a half. When b is negative 2, it's a fourth. As the negative values go farther and farther to negative infinity, the y value gets smaller and smaller and smaller. But there's no number we can put in for x that will ever give us 0 back or negative number back. So that's why y will be approaching 0 for infinity but never get there. So we have a few things going on here. We have y equals 0 as a horizontal asymptote for every exponential function. We have this point 0, 1, which is going to be on every exponential function. We have the point 1, 2, or 1b based on your function, whatever b is. And those things will be consistent for every function that we graph. So keeping that in mind now, this was b greater than 1. This was an example of the left graph on the front of your notes. All right, so now let's talk about when b is less than 1 but greater than 0. So we will do the same thing for we're going to use b equals 1/2. So I'm going to do another table. Just to show you how the math works. Same values. When I put negative 3 in for 1/2 for x, I've got 1/2 to the negative 3. I'm still flipping the base and changing the exponent to positive. Here's what that looks like now. Flipping the base makes 1/2, makes it 2. The exponent now becomes positive. It's positive 3, and 2 cubed is 8. So I have a point at negative 3, 8. Putting negative 2 in for x. Flip the base, becomes 2 over 1, or just 2. Exponent becomes positive, that's 4. Putting in negative 1 gives me 2 to the positive 1, which is 2. And here we go with the 0. 1/2 to the 0. Anything to the 0 power is 1. So my point here is 0, 1. Just like the previous graph. Now when I put 1 in, It gives me the base, whatever the base is, 1/2. So my point when x is 1, the y is whatever the base was, which was 1/2. When I put 2 in, 1/2 squared is 1/4. When I put 3 in, I get 1/2 cubed is 8. So I get 3 and 1/8. So let's look at that as a graph and see how it compares to the first one that we did. -3/8 is up here, kind of, sort of, somewhere. -2/4 is half that distance. -1/2 is half that distance. 0/1 is half that distance. 1/1/2. 2/1/4. 3/1/8. Still going to be approaching 0 forever. So I still have this horizontal asymptote. I still have the point 0, 1. Where is your point 1, comma b? Your base, 1/1/2. It's right here. Okay. So if you notice now, so this is why we say this graph is decreasing. As x goes to positive infinity, y gets closer and closer to 0. It's getting smaller. On the left side, the left graph, as x goes to positive infinity, y is getting bigger. So we say that's increasing. So this graph we say is decreasing because that's what the y values are doing as x goes to the right. And this one we say is increasing because that's what the y values are doing as x goes to the right. All right, so keep all that in mind as we look back to the front of the notes. A few things on the notes here. We won't talk about the case where b equals 1. So this only works when b is not 1. Because if I plugged 1 in for b, let's just look at what that happens. If I plug 1 in for b, then no matter what I put for x, y will always equal 1. So really this is y equals 1, which is just a horizontal line. So we're not particularly interested in that in this instance. These are one-to-one functions because they pass both the horizontal line test and the vertical. The domains are negative infinity to positive because all x values work. However, the range will always be 0 to infinity for the parent functions, if they haven't ever been transformed up or down. X-intercepts, none, because it will never cross the x-axis. The y-intercept will always be 0, 1, no matter what the base is, and we talked about that already. There will always be this additional point, 1, comma, and then your b value, which is your base, and there will always be this horizontal asymptote at y equals 0. So here's y equals 0. Here's 0, 1. There's always a 1b, whatever your base is. Over here is my horizontal asymptote. Here's 0, 1. And then 1b, whatever your base is. See how it's less than 1? Just like it says down here. And then this is greater than 1 at 0b. See how it's bigger? It's greater than 1 right there. Or the y value is bigger than 1. Okay, so looking at these examples down here, it says graph each of the following functions by translating the basic function y equals b to the x, sketching the asymptote, and strategically plotting a few points to round out the graph. Clearly state the basic function and what shifts are applied. Okay, so here's where we do some transformations. You'll be glad to know this is not trading. This is transforming stuff left, right, up and down, and reflecting. So hopefully that'll be better on your psyche than Trady was. The first thing we want to do is identify whatever the basic function is. So here's what I want you to keep in mind. When I'm asking you for the basic function, I'm asking for this form. Y equals b to the x. That's it. All I need you to do is determine what the b is and plug it in. So if you're looking at number 1, the b value is 3. Okay? This 3. Let me show you which 3. There's a few 3's on, 2 3's on there. This 3 right here is the b value. All right? The minus 2 here is a transformation. The minus 3 here is a transformation. Okay? The yellow 3 is the base. So when you go to write the basic function, you just need to write 3 to the x. Or I'll take y equals 3 to the x as well. Right? Then it asks for you to identify what the transformations are. So I highlighted those in blue. The first transformation is the minus 2. Remember, for transformations, you're kind of working from the inside out. Tells you which ones you do first or second. Generally, not every time. But in this one, it will be. So minus 2, that is coupled with the x. That's where we do insiders lie. So that means it's a right 2. Okay? Or you can write like this, right 2. And then that minus 3, that's down 3. Or I'll take this, down 3. You're going to write with arrows or with words. So in order to do that, let's graph the parent function, the basic function first. It's not really a parent function because it can change depending on the base. So the basic function graph, remember, is going to look like this. It's got 0, 1 always. And then it's got the point 1b. Remember, every exponential function has 1b. Well, what is b here? B is 3. So I'm going to go over 1, up 3. And then I have the horizontal asymptote here. Okay, that is the basic function. The shifted function, I'll do in blue. Everything's going to shift down, right 2 and down 3. So my 0, 1 is going to go right 2, down 3. 1, 3 is going to go right 2. Right 2, down 3. And then guess what else transforms or shifts? The vertical asymptote is going to shift down 3. Okay, so there is the shifted function. You pause the video while you try number 2. Okay, so hopefully you came up with y equals 1/2 to the x as your basic function. Your transformations so here, so here's your base. Here's your base. And then here are your 2 transformations, one here and one here. So remember that a negative x means you're taking your x values and you're taking the opposite sign of them. So if your x value was 2, now it's negative 2. So picture in your mind, what does that do with all your x values? It reflects them over the y-axis. So that's your first transformation, reflect over y. Then the second one is a +4. That's a vertical shift of up 4. So here's my my basic function is 0, 1 always. And then 1 comma whatever your b is. And our b here is 1/2. Okay, so I have a point at 1, 1/2. And you'll notice that automatically shows me that my graph is doing this. And I have a horizontal asymptote here. So now if I'm reflecting over y, 0, 1 stays here, because if it's reflecting over y, it stays in that spot. Okay, but then it goes up 4. So from here, I'm going to go 1, 2, 3, 4, right around here. My 1, 1/2 point, reflecting over y, puts it here. And then from there, I'm going up 4. 1, 2, 3, 4. My horizontal asymptote, y equals 0, is also going up 4. So it's here. And then I just sketch this in. And I'm done. You may begin your homework. The answer key is in the back. It's on Google Classroom, wherever you need it.